Okay, I think we'll get started. Uh, Good morning, everyone. Oh, and Becky, thank you for the note. Um, Welcome to this webinar on renewable energy resources and sustainable design that's being offered by the California Local Technical Assistance Program as part of our Sustainable Engineering Training Academy um, series of offerings. This is the fourth such class as part of the setup program. My name is Tom O'Brien. I am the director of the California LTAP Center, and we're really pleased to have you as part of this small but mighty group of learners this morning. The California LTAP Center is based at the Center for International Trade and Transportation here at California State University, Long Beach. Our center's mission is to be responsive to the needs of local agencies and state government in California with regard to transportation. We are part of a national network of local technical assistance program centers. There's one in each state, as well as in Puerto Rico, serving local, rural, and tribal road agencies. Here in California, we do this all in partnership as part of a broader network under the direction of the Division of Local Assistance at Caltrans. If you'd like to learn more about what we do, including all of our training programs, webinars, we invite you to go to caltap.org. There you can also sign up to receive our e-blast, which is probably the best way to stay on top of our ever-changing list of course offerings. One of the things that you'll also find is that being part of this national network means that those of you in California are able to take advantage of programs offered by our partner centers throughout the country. We also manage a loan equipment program on behalf of Caltrans, including retroreflectometers, and we will be having drones and traffic radar coming soon. And more information can also be found on the website. And Scott Jakovich, who you'll meet momentarily, is a principal contact if you want to explore that opportunity further and learn more about how that works. But yeah, please subscribe via the website. You'll find ways to send us emails if you have questions, to provide input on possible training ideas that you have that you don't see on our list of offerings. So please stay engaged. Today's course is on renewable energy resources and sustainable design. And as I said, this is the fourth in a series that has already addressed environmental impacts of construction, fugitive dust mitigation, and greenhouse gases. Your instructor is going to be Dr. Hamid Rahai, who is with the College of Engineering here at Cal State Long Beach and the director of the Sears Center, which he can tell you a little bit more about. But since we're a small group right now, what I'd love to do is just ask each of you to say hello, tell us where you are, what you do, and I think that will help Dr. Rahai tailor some of his comments to your particular needs and interests. And so we'll have Dr. Rahai introduce himself last, but maybe I'll ask Kevin to say hello.
Yeah, hey, how's it going this morning? I'm Kevin McDaniel. I'm an engineering technician with Public Works in Fort Bragg, California.
Excellent. Well, we're happy to have you, Kevin. And maybe if I could also ask everyone just to say a little bit about what you hope to get out of a discussion of renewable energy resources and sustainable design. So Kevin, do you have any thoughts on that?
Yeah, I am kind of interested in the topic in general, but I'd like to kind of figure out ways we can implement more sustainable design and everything in the municipality aspect of things. So it's kind of just looking to get some some info and figure out how that can be applicable for us.
That's great. Thank you. Becky.
Good morning. Yeah, my name's Becky Bucar. I work for the town of Truckee, just north of Lake Tahoe. I'm the assistant public works director, and I think I'm just looking for. I think the town's very interested in pursuing a lot of sustainable design, and I'm really kind of hoping I can get just a nice, good sort of overview of what's available and ideas. So just hoping to. I'm sure I'm going to learn a lot. So thank you.
Thanks, Becky, and welcome. Sally, good morning. Sally, I don't know if you're able to log on, and I see your mic's on. Okay. Scott, would you mind introducing yourself, please?
Sure. Thanks, Tom. As I try to work these controls. My name's Scott Jakovich. I'm the manager of the California Local Technical Assistance Program. I work with Tom at Cal State University Long Beach to bring training and technical resources to our local agency partners.
Thank you. Emily, would you mind introducing yourself and telling us a little bit about what you hope to get out of the session today?
Yeah, hi. My name's Emily. I work for the Coachella Valley Association of Governments, or CVAG. I also work on our local CCA, Desert Community Energy. And so mostly probably we're hoping to hear about how this can impact our member cities, because we're looking to implement better renewable energy infrastructure as we move forward into things like the EV space and stuff, but also just generally looking forward to renewable energy resources that we can use more specifically around our CCA community.
Excellent, thanks. And let me try one more, Sally. Sally, are you able to check in? And if you can't, maybe just type a message into the chat. We'd love to learn a little bit more about you and your work. Okay, well, with that, I'm going to turn it over to Dr. Rahai to introduce himself. And I'm looking forward to a successful session this morning. Thank you. Hamid, it's all yours.
Thank you, Tom. Good morning, everybody. Welcome. As Tom says, my name is Hamid Rahai. I'm a professor of the Mechanical and Aerospace Engineering at Cal State Long Beach. I'm also the director of the Center for Energy and Environmental Research and Services. CEERS, we have been in place more than 20 years. Our mission has been to do research and provide services and also training in the area of renewable energy, emission control technologies, environmental impacts. And we also, as part of our work, we work with the aerospace industries in our area, utility companies with SCE mostly, and Southern California Gas Company, and also with the ports. We had projects and engagements with the ports, and we continue doing that especially with the Port of Long Beach. So as Tom mentioned, that this is part of the series of the training that we have been offering as part of the CalTAP. It's part of the Sustainable Engineering Training Program at CEERS. So I hope that you can benefit from this overview of what the sustainability parameters are for the buildings, and then how we can use renewable energy and other resources to be able to have a sustainable building and have sustainable resources for that. With that, I want to mention that we have a small class. So you really, if there is any question during the presentation that you want to ask me, just unmute and ask me the question. So I'm looking forward to a lot of engagements during this webinar training that we are doing, and hopefully we can all gain something from it. And I really appreciate your feedback on this, so we can improve on this on the future training that we have. So with that, Scott, I'm going to share my screen.
Please do. And just go to presentation mode.
Yes.
There we go.
So everybody can see this? Anybody that he may?
Yes.
Okay, great. Thank you so much. So let's go. The outline, I put a tentative outline here that show you a case study as College of Professional and the Continuing Education building at CSULB that has a platinum rating and how they do it. And hopefully we can come back to this during our eQuest analysis. Then generally we will talk about design for sustainability and building energy performance simulations. Then we will talk about PV, photovoltaic system, passive solar design, solar water heating, and then building energy performance as related to the, parameters for sustainability, and also depending on the type of zones that we have. California has about 16 zones that based on that, the design is done based on the temperature, humidity, precipitations, and other things within these zone areas. We talk a little bit about the time-dependent valuations, and then we go to Q&A and maybe a break. And then we will start talking a little bit about the eQuest and a practice. And then again, another Q&A and maybe a break. And then we'll talk about urban wind energy and wind turbines and an overview of the wind energy basics and how it impacts California and how it can our local communities. And these are the new ideas also included here about the urban wind energy that that is under considerations for cities that have enough wind to generate electricity within the urban environment. And then the last Q&A, and hopefully we conclude from that. As I mentioned, that anytime that you have any questions or any inquiries that you have, just unmute and ask me the questions so we can discuss this before we go further. Okay, with that, we're going to start. So this is a CPACE building that was completed a few years ago. It's a platinum LEED certified, and I will discuss what that does mean. It's a 3-story buildings. It's an L-shaped buildings, and it took advantage of the natural lights, but at the same time, if you can look at it, it has enough shading that it does not have direct lights. So it has indirect lights to reduce the use of electricity. At the same time, that it's also mitigated the solar radiations with this shading that it has, and to reduce the load on the HVAC system, the heating and ventilation and air conditioning systems. So what are the characteristics of this building? These are the different views of these buildings. It is mostly classrooms and seminar rooms, meeting rooms, some offices there. For that, I think it cost about $20 million at the time when they finished, $21 million. And then it is a solar-ready buildings. And I will discuss what this solar-ready means, that based on that. A lot of time, when you do a building, in order to be able to get credit, tax credit, from the federal government and the state government, you go through this process of the meeting certain criteria to have a rating, LEED rating. And LEED Platinum rating is the highest that you can get. And if you have solar-ready building, that means that it's ready. The analysis has been done for this building that we can put solar panel on the top. At the present, it doesn't have that. But if you put solar panel on the top, based on that, you get a net zero building. In other words, whatever you generate, you consume. So basically, you don't use electric grid. So that's the meaning of the solar-ready buildings. So the design approach for this is that what shape the building is, where is located, what is its orientation. All of these matters because based on the solar radiation. And generally, if the building has enough area facing south on the roof, then it has the highest level of the solar potential that they can use. And based on that, we try, and also you can take advantage of the natural light that's come through, so you don't have to use a lot of lightings and electricity to be able to light the building. Then the type of windows that you use, the type of insulation, and the type of roof that we have. So when builders look at the things, initial design is, as I said, that they have to decide what shape building that you want to have and where does it sit and what orientation it has. Then windows, what type of windows that we're going to use, and what is the ratio of the area of the window to the total area of the wall. But that is kind of, and also the doors and so on, and start deciding on the percentage fenestrations here. And then the type of insulation that you can use, standard insulation for the wall and roofing, and the shape of the roof that you have. Then what kind of system you're going to use. You have a heating, cooling, and ventilation system. The rating of those systems are important. For this building, they are using the central power plant, hot water and cold water for the system. So it's a it's a central system that they use to heat and cool this building. What type of lightings? Obviously, a lot of LED lights these days that's been used to reduce the energy consumptions, electric energy consumptions. Plugging loads, plug loads is that the maximum loads and distribution of the loads that you have based on the occupancy. How do you control building energy? The type of control that you put in there. And the reason is that, for example, for this building, the occupancy is from 7 a.m. or 8 a.m. all the way to 10 p.m. So the control system starts around 6:30, 7 o'clock, and then it shut down at 11 o'clock. So we don't have any heating or cooling or anything between the 11 p.m. and also 7 a.m. So this way you can save a lot of energy. So there is a special control system. Management system is that, that in terms of the occupancy, the level of the lightings that's come on off, the sensors that you put in there to control the lightings, and also control the level of the air distribution or heating, or the fan that we have in this building to come on or off during that time. That is the management of the system. And then the passive strategies that you use, that, as I mentioned, the window is what type of window, what type of lighting that you have, and how do you dim the lights according to the lighting that's come from outside, and other things. And then what kind of renewable energy sources you're going to use for this. Obviously, in our area, there's not much of the wind that we can use wind energy. Solar is the only options. And also the water saving options that we have, because we use central power plant and so on. So what kind of renewable energy, in case it's the solar system, so we have a solar ready buildings that we use. So detailed design, optimized load, optimizing in order to reduce loads, we optimize building footprints. Initially, I remember that this building was 20-25% more than what it is now, and the initial design, but after assessment of the usage and the footprint and all this, then the size of the building was adjusted accordingly. And obviously also the size of the building is related to the cost, that depending on how much budget we have, so on. Orientation of the building, it was decided that it can be orientation in the L shape, because major part of the building is facing west, so in the afternoon you have this sunshine, east and west So you have the sun coming in, so you can take advantage of the daily lights for that. And then the other side of the building is oriented toward north-south. That north-south is you get indirect light automatically, which you benefit from that. So you can see that when part of the buildings has shade, has these screens in front of them to take down the direct lights, but the other side does not have that because it automatically gets the indirect lights. Then obviously, so that's the orientation. Efficient envelope of the building is the location of this, is that based on the campus site and so on. So that's where access is. It's very accessible to the students and also the public. This building has been used for also many training and meetings, both from the campus and from outside. So depending on that, so where it's located. And so 95% spaces have natural daylighting. That's the design of this, that you don't have a dark spots. You have, especially except for utility areas that that house the utility pumps and other things. Generally you have natural lights everywhere. In order to decide on the system, if the system has radiant heating and cooling system, so it has coils on the floor that hot water or chilled water that pass through, and this is how they actually heat or cool the buildings. It has fans also to recirculate. Fans are low level cost of energy consumption. So if you can use fan to recirculate the air within to make the temperature uniform within the room, then that is the best option that you can have. LED lighting with occupancy control, as I mentioned, that if if the lights come on when there are people present and it goes off when they are not. And then also it does daylight harvesting, because it dims when there is enough daylight to light the room. So when it dims, it consumes less electricity. Mixed mode ventilation, natural ventilation, and those systems. And natural ventilations is that obviously from outside, and also the fan, and then also the direct the system that we have that for the water, cold water and chilled water, and also the hot water system. So the occupancy controlled power outlets means that the HVAC system that we have that also come on and off depends on the occupancy, so it can control the temperature. So you set a certain level of temperature, and based on that level of temperature, it come on and off to control how much energy is consumed. Photovoltaic system on the roof and over sustainable landscape areas. So it's, as I said, it's a solar ready buildings. And also around that, we have enough vegetation and trees and planting to be able to absorb heats and generate a fresh environment. So based on that, it creates a reduced temperature within the envelope, around the envelope of the buildings. So especially vegetations, it absorb heat for sustainability. So it could produce a first pleasant environment. At the same time, it actually cool down the surrounding environment. So a specification for these buildings, that this is the annual consumptions. It's presented in terms of the energy use intensity. And I explain what the energy use intensity is in a moment. But that in order for you to assess a building, you would like to look at the energy consumptions and water consumptions. So if you look at this, the electricity, that it increased initially, the building opened up in 2021. And for the first year, the occupancy was not as significant. So 95,000 kilowatt hour energy for electricity, 15,000 plus for the chilled water that was used to cool the building, and then about 35,500 kilo BTU British thermal unit that's used for the heating the building using hot water. And when we look at the BTU here, is that how much natural gas was used to heat this, and also the chillers, how much electricity was used to chill the water. This is how you calculate those. And so for the total for the buildings came out to be for 2021, 546,721 kilo BTU. And the way it calculated the equation on the lower part, it says that it converts the electricity to BTU, and the tonnage of the chilled water from the chillers times 12, and then the BTU from natural gas that was used for hot water. Add them up, and you get the total kilo BTU of the energy on annual basis. And then you need to divide this by a square footage of the building, which is almost 38,000 square foot of the building's conditioned area of the building. And then you can see that you get an EUI of 1439. And then it increases because of the increased usage of that. And for 2023, it was close to 25. Now, why this is significant when you assess the building is that because if you look at, and I'll show you that the general expected EUI for educational institutions such as ours is around 50. So that's it. So 25, 50 is 50% of that. That means that the energy saving is significant here, that when you look at this. So the way to assess any design based on expected usage of that is to look at the energy use intensity and then divide that by the footage, total square footage of the building. And that gives you an idea of whether you are in compliance or you are not in compliance. So what are the design for sustainability, design considerations? Well, total energy used and intensity, time variation targets. That's from the, I show you a table that you say that I want to meet this target, EUI target for this building. What do I need to do to meet this EUI target for this big building? A big trend here to take advantage of energy use modeling. Energy use modeling, as we will discuss later on, is that a way to look at time variations of the energy use and also annual energy use of the building. Energy use modeling should be done at the beginning. That's the best way rather than later on, because later on, if you want to do modification to the building, it's generally much more costlier than doing this at the beginning for the new building. It's doable. There are people who will do this for you, but it is generally costlier to mitigate anything on the existing building to be able to meet these criteria. It meets these energy targets. So it's not building simulations, building performance simulation could reduce the first cost, operation cost, and environmental impact for the life durations, for the life of the buildings. You can do that. So it is extremely advantage to do this at the beginning before you do anything, because you can play around with the different options, that you have. When you have an orientation of the building, if you change the orientation, what happened? If you change the window or insulation and the type of roof that we have, what happened? That if the use of the fan is preferred inside, how does the fan affect the temperature within the room when you have this kind of cooling system or heating system and so on? So it gives you an idea of a good estimate of the energy usage if you meet your target with this design. So what are the design considerations for optimizing energy performance? Is that, first of all, we need to look at the energy efficient HVAC and refrigeration systems and usage schedule. What kind of natural ventilation we can use. So this is a kind of, if you are an industrial zone or in the area that needs extensive filtration, obviously natural ventilation is not an option for you. Because, especially, that we look at the buildings that are within the trade corridors, near the ports or near industrial zone and so on, there is a lot of pollutions coming out. So if you want to take advantage of the ventilation in this area, obviously you're sucking in a lot of pollutions. And so you need a kind of filtrations. But if you are in an environment that you can use natural ventilation, that helps you a lot in terms of the design. Solar orientation of the building. When you want to take advantage of the solar radiation for solar system, that the best, the highest amount of electricity that you can get when the solar panels are facing south. So you need to look at to see that, for example, in Long Beach, the best is if it's faced south and solar panels are at an angle of 15 plus latitude. So we are about 35-degree latitude, plus 15 is 50-degree latitude. So if you orient your solar panel facing south at 50-degree angle with respect to horizontal, then you get the maximum radiation out of it and the best efficiency out of it, and the maximum electricity can be generated. So the orientation of the building becomes important in this case. And also that if the building are mostly in north-south orientation, that the sun comes from east and go down in the west. So you always get indirect lights. So you don't get direct lights from solar radiation. In terms of cooling and heating, you are in much better situation, especially if you are in a hot area. But if you are in a cold environment, let's say you are in Denver, and you want to take advantage of the solar radiation to heat the buildings so you can have less fuel use during the winter season, then obviously your orientation would be different. So you want to take advantage of that. Daylight and shading, use of skylights is highly recommended, and to reducing direct solar light in hot climate. As I mentioned, in cold climate, direct solar is used to reduce heating load. Use of renewable energy sources. Wind, obviously, wind, it depends on the utility companies whether they use wind as a resource to generate renewable energy. Solar is the one that I'll talk about, the solar energy potential of the buildings. Overall in the US, we have significant potential for electricity generated by solar power. And then biomass is that, if you burn woods and trees, and so on, and then obviously with certain filtration, you can generate renewable energy. Micro hydro system, we don't have much in California, but there's a lot of places that they have dams and small dams and so on, and they use that one as a way to generate electricity. Obviously, the biggest is in Nevada, that we have a huge dam there that generates a lot of electricity. So you take advantage of solar systems. It's a rooftop solar photovoltaic to generate electricity, or solar thermal system. I'll talk about that in a little bit. And making the building solar ready if a solar system is not installed. So if it's costlier at the beginning to put, or you don't have any budget to put solar on the top, but you want to have it solar ready. Then in the future, when you want to install, then you don't have that issue. You don't have to do any kind of mitigation of the roof or system, assembly or connections to install a solar system. So that is, these are some of the parameters or design considerations. I think somebody's coming. Any questions so far?
I have a question. This is Becky.
Hi, Becky.
Hi. You talked about biomass.
Mhm.
That's something the town's sort of been looking into. It seems like something that's becoming more and more popular. Can you talk a little bit about like what you typically see for biomass applications? Is it being used for heating, electrical generation? I mean, how are you, as for municipal buildings, like how are you seeing that used more recently?
So Southern California Gas Company has actually a plant. It's a pilot plant to generate with the biomass, and it's not just burning of the waste. It's also harvesting gas from the waste. So methane is generated from the waste, from the landfill and so on. So a lot of time they harvest that one and they use that to generate electricity. So right now it's on the pilot scale that they want to see what the efficiency is, how they can fine tune the system and do that. But but if you use burning of the woods and other waste and so on, then there are certain standards for filtration systems, so you don't have emissions coming to the atmosphere. And that one also, there are some small scale in Long Beach. I know that city of Long Beach uses for some of the waste that they have and so on to generate electricity. So there are plants, but it's not very popular or extensive right now.
Thank you.
Oh, you're welcome. Any other question? Okay. So we talk about LEED certifications and consideration for LEED certification. And I mentioned the building that we have is a platinum, has platinum certification. It's a platinum certified. It's the highest that you can get. So project points are earned by adhering to design that address carbon, energy, water, waste, transportation, material health, and indoor air quality. In other words, that you get points for these parameters. If your design reduces carbon footprint, then you get points for that. Energy consumption is reduced, as I said, that if your EUI or energy use intensity is low, below the standard, then you get point for that. If you are using water saving equipments, in showers, bathroom, and so on, you get point for that. Or you harvest the shower water for irrigation, you get point for that. If your waste is low, or you can manage to reuse your waste and so on, you get point for that. If you are in a building that reduce transportations, a lot of time when municipality or federal government and so on, they consider or issuing permit for any kind of building, they look at this to see that if having this building reduce any kind of traffics and reduce transportations, and is it close to public transportations? For example, buildings, a lot of apartment buildings in downtown, that this cause people to live close to the work, and if that says, can they walk to work, can use public transportation to work, and so on. And if that does, then you get point for that. The type of material if you are using recycled materials. Materials, especially if you are using materials with high embodied energy, then if you use recycled materials, then recycled aluminum, recycled iron, recycled, the concrete, and so on in your building, then you get point for that. The quality of the health of the indoor air quality and the health of the building and so on, you get point for that. So as I mentioned, platinum is the highest. If you get 80 plus points, you get platinum. Between 60 to 79 is called gold. So silver is 50 to 59 points. And then it says LEED certified. And when they say the building is LEED certified, it has somewhere between 40 to 49 points. Example of the points. As I said, that performance-based indoor air quality design and assessment up to 7 points. You get that? That if you are, for example, you have an exercise room, you have within the building that the employee can go and exercise, and it has a good indoor air quality for that, and they can, that it's a healthy air quality, you get point for that. Design for enhanced resilience, up to 2 points. So what does this mean? Is that you design that you don't have to mitigate the type of roofing that you put in, the type of external wall, internal walls, the system that you put in there, that it lasts a long time. If it lasts a long time, up to 2 points for that. Low carbon construction materials, that, as I said, that those materials that we use, if they are high embodied energy, that means that a lot of energy has been used to produce that kind of, like aluminum, that like iron, like cement. These are high embodied energy material. So if you use recycled materials, that means that you cut down the embodied energy or production by so much. That means that you are using low carbon construction materials. So it's up to 2 points. Whole projects, water use reduction, up to 10 points. So you can see that if you put water saving equipment inside the buildings, the shower, the toilets, all the, others, sensors that you put in, that for the sink, that when you use the water is not running all the time and so on. So, and also you use recycled water for irrigations, for other use than drinking, then you get a lot of points for that. You get 10 points for that. Offsite rain water management, up to 3 points. On-site carbon sequestration through planting, 1 point. That I mentioned in our previous webinar that you can use 3 for carbon sequestration. And by the way, maples trees are the one with the highest level of carbon sequestrations. And so if you have maples trees around your buildings, you show that, you demonstrate that as part of your design, you get point for that. Passive survivability and backup power during disruption, up to 2 points. I show you when I talk about the solar system design, you see that there are backup batteries there. So you can have backup generator also, but these are when you do design and you have this kind of backup systems, then you get point for that. These are some of the examples of the points. There is a huge list of those when you do design that you can go through that. But among all the listing that I have here, obviously you can see that when you do water use reduction is the highest. So if you 80 points, that it is more than 10%, if you do this, and you get good points for that for the LEED rating. So I talk about using building energy performance at the beginning to assess the type of energy, the amount of energy you use, the type of activity you have, because that helps you to meet your design points. So what are the things that you need to consider? Climate condition and thermal comfort. There are certain in each area each zone, climate zone, there are set temperatures for heating and cooling and indoor temperature and based on the outdoor environment. So design is, the initial design says consider that what are the set temperatures that you want to have for your system. Then what kind of solar radiation and shading requirements you need to have in order. So when you do any BEP, Building Energy Performance Assessment, you can actually play around that based on the site that you have, is that, you know, that how can you reduce direct solar radiations in California. Obviously, if you are in a cold environment, you want to increase that. And then what kind of shading that you want to have. Do you want to have outside shading? Do you want to have inside shading? Is it automatic shading? Do you want to have a windows that have films on in them that they can cut down radiations, and so on. So daylight harvesting, you know, and that's another issue, that you can see that how much light you can get during the day on hourly basis that come to different area of the buildings, and how can you use that one as your at your advantage to reduce the energy cost. Massing and orientations, you know, the building size and orientation of the buildings are the one that you look at to see that to meet your needs. Appropriateness of natural ventilation. I mentioned that if you are in an industrial zone with high pollution surrounding the buildings, then obviously natural ventilation may not be an option for you. But then in a lot of areas in California, you can take advantage of natural ventilations and also use fans, you know, to recirculate and you know, make temperature uniform within the conditioned environment. And building health and safety, you know, what kind of material you have used and how safe they are. Indoor air quality, what type of indoor air quality that you have. All of these, you know, become part of the building energy performance. You can actually do the simulations and get all these, an idea of all of these at the beginning. Before, you know, proceed with the design and, you know, final design and constructions. So building performance simulations, as mentioned, is the elements are location, climate and weather information, that's air temperature, humidity, wind speeds and direction, solar radiation, precipitation rates. HVAC equipment and their use schedule is also identified in the building performance simulations. Internal load schedule. So, for example, for our buildings, at 8 o'clock, the load is different than, you know, at 11 o'clock a.m. And also in the afternoon, the load is different. So, depending on the load, you can control HVAC system to meet your load requirements. So this way, you don't have a fixed amount of the air coming in and going out to alternate. You know, you meet the load according to the internal operation or internal occupancy. And based on that, you can also save energy. The building envelope, window dimension and location, window to wall ratio, external and internal walls, materials, painting, shading, etc. And then the last one is building shape and orientation, height and floor area, building function, heights between the floor and the top floor to the ceiling. Do you have attics or not, and so on. So all of these can be assessed in building simulations. On the picture on the left-hand side, if you look at this, for the top building, for the top floor, you can see that there is overhang shade that is put in there. That is to cut down on direct solar radiations for the overhang. Sometimes you have it this way, sometimes you have it in between the floors. You know, you can see that this is shipping receiving areas, that on the bottom you have actually a shading area, so you don't have to worry about the solar radiation on the top, on the, you know, the first floor, but then the top that there are offices and occupancy area, you have to worry about those. I talk about energy use intensity, as I mentioned, is the total energy that include energy used for HVAC systems and also electricity of the system for heating and cooling condition in the unit of the kilo BTU. BTU is energy required to raise the temperature of the water by 1 degree. That's the definition of the BTU. Kilo BTU is 1000 BTU. And then you calculate this for 1 year annually, and then divide by a square footage of the building. So that is the energy use intensity. That's how you calculate that. And that give you an idea of whether your building meet the performance that you need in order to have a good energy performance. So I mentioned that what are the national median reference value for this EUI? That let's look at this. Here we have a source and site designation. Site is primary energy, source is combined. That means combined energy and water usage in the single unit. So here also that the water usage is also incorporated in kilo BTU per square footage. So if you look at this, for bank branch is 88.3, for example, for the site EUI. For financial offices, 52.9, K through 12, 48.5. If you look at the other education, that is like a public education that we have and other things, it's 52.4 and so on. So for the building that I mentioned at the beginning, that with about 26 EUI, we are 50% of this. That means that that's why it is a platinum LEED certificate building. And by this, now I want to talk a little bit about digital twin. Digital twin is nowadays there is a lot of discussion about digital twins. The reason is that because of the technology advancements and computer power that we have, we can generate a digital twin of the real building or real system. In nuclear power plant, in conventional power plant, gas or coal or other things, they already have been using this. This actually started about 10 years ago. It was, proposed some time ago, but the use of this started 10 years ago, and it's becoming popular for other areas. And it's not just the digital image of the building. It's actually, it's a digital twin that functions like a real things. Of the system with everything. For example, in a power plant, when they want to assess whether they need to change the pump here and there, they can look at digital twin, change the pump digitally, look at the function of that to see if it works, or if they want to put any kind of sensors within the building, they can put that, run the simulations, look at this. So it's actually a virtual building that replicates the real building, mimics its performance, and is dynamically updated with data from its physical twin and the environment. It allows testing the impacts of various design criteria and systems on the building performance and living conditions under various climate conditions for an optimized design. Right now, the services that provide this kind of, the companies that provide this kind of services are very limited. As I said, this is at the beginning, this technology is, it's at the, infant stage right now in terms of applications. And so you will see that the architect firms and engineering firms and so on, beginning transition to this kind of approach before the design is finalized, to be able to make sure that you meet all the requirements, especially in terms of sustainability, to be able to have a sustainable design. So I'll give you some background on electric power sector, electricity generations in the US. This is the data between 2010 and 2022. So as you can see on the left-hand side, use of coal has gone down quite a bit. Natural gas has gone up to offset that. Renewable has gone up to offset that. But nuclear is flat on this in terms of the sources of energy productions. In terms of the renewable, you can see that wind has gone up to being the highest. After that, the hydro is kind of stay flat based on what there's no new power plants. Solar has gone up, biomass is flat, and geothermal is flat. Geothermal, by the way, is taking advantage of the heat, underground heat, when there are reservoir of the heat underground, and when they do explorations, that they use that one to heat the water. And if there is enough heat underground that they can tap into that, they can generate a steam, and then from that steam, they can generate electricity. Some more information by the, when electricity generator by major type and share of the total annual US utility scale net electricity generation, this is in for 2022. A steam turbine, a single cycle, all sources amounts to 42.5%. So of that 42.5%, 19.4% is generated by coal fuel, 18.2% nuclear, 2.6% natural gas. Even though it has increased, it doesn't generate, it's not there yet in terms of the generating electricity. And biomass is on the same order of 2.3%. Natural gas combined cycles, it's grown quite a bit. That is 33.8%. 21.4% is from combustion turbine. That means that we have a combustion to heat the water to generate a steam, to generate steam and generate electricity. Or we use combustion turbines, that it's actually use natural gas to rotate and generate electricity. Then we have a steam turbine, and then we have a dual or single shaft turbines, and so on. And then of these combustion gas turbines, single cycle, if it's just a one unit, natural gas usage, 3.6%. But I want to bring your attention to wind turbine. All types of wind turbine amounts to about now 10.3% of this. Hydroelectric turbines, 6%. Photovoltaic, which solar that is promoted, and there are also tax incentive to do this, is 3.3%. There's not much of the storage system yet, but hopefully it grows quite a bit, so we can have a backup storage system using solar or wind or renewables. There is potential for generating solar energy. This is, I mentioned that in the previous slide, that photovoltaic amounts to 3.3% right now, nationwide in 2022, using solar power to generate electricity. But what is our potential? That we have enough spaces, roof, for generate electricity. If you look at the building's footprint, if they are smaller than 5,000 square footage, their annual generation potential is 25%. Medium, between 5,000 and 25,000 feet, about 5%, larger than 25,000 feet, 8.2%. All building combined, more than 38% of the electricity within the US nationwide can be generated by solar. You know, we are at 3% right now. So there is so much more we can generate using our rooftops. That's why there are incentives from federal and state government to use solar. And the cost of solar has gone down. I'll talk about it in a moment. So there is a lot of potential. So that's why that at least having the building solar ready is extremely important, because that you could add solar system to that for generating electricity, or at least partially offset the cost of electricity or the needs of electricity for the building. In terms of the states, California has the highest annual generation potential. The previous slide gave you nationwide, but California can produce 74.2% of electricity from rooftop PV. That's almost there. We are almost there. With combined with wind energy, we can go 100% renewable. And then after that is Maine 60%, Vermont 60%, and it goes down depending on, Wyoming is 14%, 14.2%, and so on. And as I said, in continental US, total is 38.6%. So, any questions so far before we transition to PV system? Any question? Okay. Well, let's talk about PV system. The efficiency of this PV system is between 15% to 25%, depending on the type of semiconductor material used. Those used in space applications such as satellite system have a 50% efficiency. As I said, that for those that we use for rooftop is somewhere around 16 to 20%, depending on the type that we use. In the 3% that I mentioned, amounts to 142 million megawatt hour of the solar generated, of electricity generated by solar PV system, solar system in 2022. So solar cells, silicon solar cells, lightweight, reasonable price and efficiency, used in rooftop and portable applications like parking lots that you have seen, often. Then there is a thin film solar cells made from very thin layer of the semiconductor, flexible for a small application, such as window installation or on a backpack that people use, to generate electricity. Then there is a type 3 to 5 solar cells, more expensive, has higher efficiency, used in satellites, unmanned aerial vehicles, and others that requires a high power to weight ratio. I also mentioned passive solar design, harvesting the lights. This is an example of passive solar design that you can see a hallway that is surrounded by the windows and with different directions, and you can see actually harvest lights from different directions. And then no mechanical system is required. The building should have south-facing windows to effectively use solar radiation to collect and store thermal mass or heat. The design should have the following elements: aperture and control, large window glass area that are facing south or within 30 degrees of the south direction and are not shaded between 9 a.m. to 3 p.m. It allows sun to heat inside the building. Use window cover or overhangs to control or block light during the summer month. As I mentioned, for example, in cold environment that you want to harvest the sun, this is a way to do it. So you can reduce your heating load quite a bit use materials with high thermal mass, concrete, stone, tile, brick that absorb heat during daylight and release it at night during the winter season, and absorb heat inside during the summer season. So actually it's cooler inside during the summer. Use natural ventilation or a distribution system to maintain a uniform temperature. Distribution system is like a fan, a ceiling fan. Solar heating system, water heating system, we don't see it as often as it used to, but it's something that is used mostly for heating the pool. These days, you can see that. It's used to reduce utility bill. It uses solar radiation to increase the temperature of the water before it enters the water heater. Less energy is used to heat the water and thus lower utility bill. Use a pump to circulate water, not very expensive and is less efficient. So basically, you have it on the top of the roof or somewhere that you can absorb solar radiations. Within that solar collectors, you have this piping system. It's also painted black to maximize solar absorption. And sometimes it has reflection systems and so on. And then, you heat the water, you pass it through the storage system tank. If you use natural gas to heat that, the amount of natural gas that you use to heat that would be less because the temperature of the water is much higher than a cold water. And this is the example of the pool heatings, that system that you can see. You have solar collectors. It's the water is go through this solar collectors that has a piping system that it absorbs heat. Then it's fed to the pool heater. So if the temperature is high enough, the pool heater does not work. So it just feed to the pool. If it's not high enough, then there would be heating, but the amount of heating would be much less. Now let's talk about the rooftop PV system. Any question? Anything? Any question, everybody? Okay. Well, this is a typical residential building that you can see, or office building. It has solar panel on the top, and there is a solar is direct current system, and the electricity that we use is alternate current system that we have in the house. So it needs an inverter to convert that. There's a breaker panel to control that, obviously, to control the electricity and so on. But then it's actually go to a meter, which is net metering systems. Net metering is the difference of the electricity generated from PV system and also from the from electric grid. And so that's how you cut down of the usage, electric usage of your house. Just want to tell you that, that for a typical residential housing and residential buildings, it's the usage of, electricity usage is about 20 kilowatt hour per day. So if you have a solar system that can generate that, then you don't need electric grid. With the backup battery system in California, that's sufficient for the building. Now, the area that you need to generate that, I'll show you a table that how much it generates per panel, and so on in a moment. It come back to how the roofing is designed to be able to take advantage of this solar system. And that from the beginning, obviously in California, we have a lot of residential building that was built way before. So they're trying to use the existing building and adapt it. So not all of them have enough surface area on the roof to be able to take advantage of this. But, obviously for the new residential and commercial buildings that they are building, it is becoming a kind of mandatory to make it solar ready buildings. You know, even when the builders do not put solar panel on the top, there are consideration of enough surface area that it can be put on the top roof later on to reduce the electricity bill. Solar cells, you can see that I mentioned about the solar cells, about 6 inch by 6 inch. 60 solar cell panels, about 3.3 feet by 5.5 feet. And then 72 solar cells are 3.3 times 6 by 6.5 feet. And it's about 40 pounds per panel for the 60 cell or 72, 40 to 50 pounds. The thickness is about 1.5 inch. As I mentioned, average household consumption in California, the annual one, monthly one is 500 kilowatt hour, assuming 5-hour sustained sun radiation. If you have, excuse me, a 4 kilowatt system, it provides 600 kilowatt hour per month, and that's more than 100% of the household's electric need. So how can you provide 4 kW system? What are the size? So here are something, a solar panel wattage. If you are 100 watts solar panel, it's 41.8 inch by 20.9 inch. It's about 6 square footage. So if you have a 6 square footage roof type, you can put a solar panel 100 watt generations. If you go all the way down to the bottom line for 500 watt system, it's 27.5 square footage. So you can see that, generally a rule of thumb is that, if you have for every 100 square footage, you generate around 1 to 2 kilowatt. So if you have an area about 10 by 10 that generate 100 square footage, or somewhere close to that, then you can have a 1 kilowatt or 1 kilowatt to 2 kilowatt system, depending on the type of solar panel that you use. And as I mentioned, that you need 4 kilowatt system to be able to generate all the electricity that you need for the residential building. There are 2 ways the system is laid out for the residential. DC coupled solar plus storage system. This is good for new installations, for new housing and so on. So you can see that DC voltage from solar panel and the backup battery are supplied to the battery-based inverter. So here, I don't know if I can use my pointer here. Here is the solar panel. Here is the battery storage. They both come to the battery-based inverter. And so they go to the house. There is also extra that goes to the main circuit breaker that can go either to the house access or go back to the electric grid. Then there is another design, this design, that the solar generated, it come to the critical load sub panel. This is the inverter to convert this from DC to AC, come to here, and then battery-based inverter is also generated, come to here, and then it's fed to the house for usage. But here also that, if there is, if we didn't have, it's a cloudy day, we didn't have enough sun, and then the energy storage go down, then, the grid electricity is used to charge this battery also, as well as supplying the house with the electricity. So this is another design for the existing system that, in the first one, we have a net metering. In this one, we don't have a net metering. uh, to take advantage of the difference or earn some money. Sometimes if the net metering allows us to generate excess electricity, you can actually get money from the utility company. So I'm going to stop here a little bit because just wanted to give you a break. It's been a long time since we talk about this. Any question you have?
Hamid, Sally's got a question.
Yeah, sure.
Can you talk about whether, there's been a big popularization of lithium batteries as taken over the storage,
Yes.
particularly for storage systems. Is lithium, even in industrial applications, does that turn out to be a better storage medium than acid batteries?
Absolutely. The storage capacity continuously being increased based on the packing, the way you pack this. If you look at the lithium battery that are used for the vehicles, now for electric vehicles, the major issues, challenges that people have right now or companies have is that how you pack the batteries to increase the range of the electricity. So because you can pack lithium sheets or parts close to each other, but the problem is the cooling of this, and also how you connect them in series or parallel to be able to generate or feed electricity or meet the need of the vehicle. So, but it's growing quite a bit. It's becoming more efficient. There is also research into lithium air batteries is going on right now that based on a patent that was issued in 60s. It is not functional yet. It's at the research or laboratory stage right now, but lithium air batteries rather than lithium ion batteries, lithium air has 5 times the capacity of the lithium ion right now once it comes to the market. So you can see that the potential for growth is significant. The potential not only for the backup storage, but also for increasing the range.
I have 2 questions.
Sure.
One, do you have any data or any insight on how well commercial buildings have been able to adopt solar and storage? I used to work for a solar company, and there was a little bit of trouble with availability, and there was also a little bit of trouble matching capacity needs.
So up to a few years ago, we didn't have any plant in the US to produce batteries, lithium ion batteries. Everything came from mostly actually Korea. Okay, so a few years ago, there were 2 grants issued for development of the solar batteries in the US. Currently, I think there are 2 plants are developed, one in the Illinois area and another one I think is in Michigan. That is trying to, so that they try to address the availability and also domestic production of that right now. So that's why, and the cost was high because of the import and coming from overseas. They are trying to cut down the cost. Once the costs go down and the capacity go up, and then it's become very viable options. That right now the cost of electricity hovers around the 25 cent kilowatt hour. That I think that now the batteries has not been able, the backup batteries and the solar system has not been able to get down to that level yet. The cost of the solar system has gone down to $4 to $5 per square footage installed, somewhere around that. I had slides for that. I thought that one not. Yeah, here it is.
Yeah.
Yeah, you
Okay.
can see that the cost has gone down. This on the left-hand side.
That's been our experience, is that it's been cost prohibitive, and then also the storage capacity wasn't quite what they needed. And I live in a very hot area, so our AC load is insane. Our average system size is much higher than the rest of the state. And then also availability has been a problem.
Yeah, but I think that within a few years, the availability, because of the domestic production, the availability will be much more, and also the cost will come down. Solar used to be like $11 to $14 per square footage. Now, per watt installed. Now it is about $4 to $5 per watt installed. If you look at this, average cost is somewhere around $4.2 per watt installed. With incentive that the state and federal are providing, it cost has come down quite a bit. Generally, if you have a large surface area, the cost is lower. I remember after the San Onofre power plant went down for the Edison, they were looking for the large roof areas to put solar panel, and they were looking at the warehouses, a lot of warehouses that we have, especially inland, to put solar panel on the top, free of charge to the owner, by the way. And they were promoting this idea that you can generate electricity to consume your own, and then the excess can come to the grid for us. So this kind of arrangement is been going on for a while right now. So hopefully, yes, I mean, it's going to go down quite a bit.
Thank you. And then my other question is, it's just related to lithium and ultimately storage. Do you know much about what's going on at the Salton Sea with the kind of the lithium valley is what they're calling it, and they're hoping to be able to
the
mine that lithium?
cost of producing lithium is it's high right now. Antelope Valley is trying to become a hub for the lithium battery productions, and so on. Because of that, you are trying, different methods of extractions to reduce the cost and so on. So it's an ongoing, but it's a huge project in Antelope Valley.
Yeah, there hasn't been much movement on our end. We live about an hour away from that area, but I have some concerns about the lithium mining in general.
Right?
Yeah, but that there is an environmental concern that they have to meet. So it is part of the city planning to develop that and invest in that. Federal government is also investing, a state is investing, but as I said, it is right now cheaper to import
Okay.
than produce right now because of the environmental concern and also because of the cost. Okay.
Thank you.
Sure. Any question?
Hello, this is Sally.
Hi, Sally.
Can I ask you about the environmental concerns on the big solar arrays that we're having? Have we done any studies on the impact of the earth underneath those panels? Especially like the farmlands where we have a lot of the panels out there. What is the effects to the soils and regrowth of the food afterwards?
It is one major. I know that Department of Energy and also Department of Agriculture have a major study in this area. It's an ongoing study of the impact of these solar panels on vegetation and also on animals. Right now, it's ongoing things. The preliminary results that I have seen from these studies is that it's not impacting vegetation as much. In terms of the animals, I haven't seen much of a data on that. In terms of, because that's a long-term study how it impacts their milk productions, or how it impacts the quality of the meat, how it impacts the health of the animals, and so on. But other than that, I haven't seen. It's been used for shading too. There is something else also I want to mention, that solar panels, the back of solar panels gets to about 150 degrees Fahrenheit. So there is some radiations coming from the back of the solar panels. It's contained with aluminum plates sometimes. There is a design that they use to pass piping under that with water passing through to cool it down, at the same time take advantage of that heat to increase the temperature of the water, and for other purposes, hot water. There is some design in that area is going on, but so there are concerns. There was a study done by also University of Denver on this one. I saw that as the recent meeting, APS meeting, presenting and so on. So it is an ongoing. It's not conclusive yet. I can say that based on what I have seen.
Thank you. I do like the idea of heating the water underneath the pipes, using that radiation as a byproduct.
Yeah, we actually did a simulation. There was one of my students did a master thesis on that. We wanted to see that if we can use that heat to increase the temperature of the water before we generate a steam for any kind of electricity generations and so on. The efficiency is very low. It's the cost to benefit analysis we did for that after the design and simulation and everything. It doesn't worth it at this time to do it. But in terms of the hot water usage, that's viable. In other words, that the same way that solar, heating system is used, this can be used to generate electricity at the same time to heat the water to reduce the utility bill.
Thank you.
Thank you. Any other question? Should we take a break, Scott?
We've got 30 minutes left to meet. I recommend we just plow through.
Oh, okay. All right. Everybody's okay with that?
I'm good to continue.
Okay. All right, great. So let me go back. These things I wanted to mention that is promoted by the Department of Energy, heat pump cycle for usage. This is the building that use PV system and renewable electricity. It's a, heat pump can be used for cooling and heating, both. Depends on how you use it. There's an expansion valve that you can switch. And based on that, and this is a picture of these heat pumps. It's a low electricity usage. So that's why it's highly promoted by the Department of Energy and California Energy Commission to use this, especially for building with solar panel. I just wanted to mention this, that when people are trying to select HVAC system, this is an option. Obviously, it's not as efficient as in terms of cooling as chiller, but it meets the need of the residential and most of commercial buildings. This is another heat pump system just for the heating cycle. You can see that outdoor coil sucking it in, and then there is a compressor that is actually compress this, increase the temperature, and then feed it through the the unit inside the building that has a fan, that then hot air coming out, and that's how that they use this to heat the building. But if you reverse it, then there is a cold hot air is rejected to outside, and cold water is, cold refrigerant is passing through, and then you can use that one as a cooling of the building. So the system is reasonable in price, it's efficient, low electricity usage, and I was looking at some housing recently to assess their characteristics and so on, and I saw that they did zoning, and for each zone they put one of these units there, and the amount of electricity that they use was significantly lower than putting a package system in there. So I already talked about this. The only thing I want to talk about here is the capacity. If you look at in California, I have a picture of California in terms of capacity to generate electricity, megawatt. You can see that and on the left, and then on the right also the figure that in terms of the cost per watt of the system, that is somewhere between $4 to $5 per watt. When we look at building performance analysis, there is a standard code that is used. It's called Title 24, Part 6. That you need, any builders to want to get their ratings, they use this code, and there's a spreadsheet that they have to fill out in terms of the energy and water, energy usage, water efficiency, indoor air quality that I mentioned before, and then additional modification to the existing buildings. So there are certain mandatory requirements that they have to meet. Every building has to be there, and also there is a performance standard in terms of energy budget that again changes by climate zone. There are 16 climate zones in California and building type. Alternate to the performance standard prescription package that provide a checklist compliant approach. So there are description of all these in the, if you Google Title 24 Part 6, it's a huge document. It's a big document. That so builders actually go through this to meet the mandatory requirement, and then any additional requirement give them credit for the building performance. The mandatory requirement, the solar zone total area shall be comprised of area that have no dimension less than 5 feet and are no less than 80 square feet for each building, with roof area less than 10,000 square foot, or no less than 160 square foot for each building with roof area greater than this. So there are certain, I just want to, I put all this information there. It's just a sample of the information from Title 24. Just to pick the solar family residence, the solar zone shall be located on the roof or the overhang of the building and have a total area of no less than 250 square footage. That's a solar ready building that they have, that it's kind of become kind of mandatory to meet this area. Low-rise and high-rise building, hotel, motel occupancy, and non-residential buildings provide, again, that is a 250 feet of the building, or it could be also in the parking lot installation. They can meet this requirement if the parking lot that has shading, that has solar panel, for a lot of areas that you can see these days that they have this kind of solar panels. I don't know if you have been in Long Beach Airport. Long Beach Airport has these kind of solar panels on the top parking structures as a way of shade and also generate electricity. And that we actually did the preliminary design for them. We did a before they proceed with any kind of analysis, and that was a few years ago. Exception, there are some exceptions that the builders can use to, if they don't meet these requirements. When it has domestic solar water heating system, you get credit for that. If there is not enough area, it has a 3-story or more with floor area less than 2,000 square footage, with the solar zone less than 150 square footage. Sometimes, if you look at the buildings and roof types, there's not enough area for them, and there's no overhang to be able to put solar panels. The building with designated solar zone area less than 50% of its potential. They have also a special control system, which is the demand response control system for controlling appliances and lighting system and so on. They have a rainwater catchment system. And so if you install that, you get credit for that, and also, you can take advantage of the exception. Having an alternative plumbing system that allows water discharge from shower and dishwasher with proper remediation to be used for irrigations. As I said, so I know our campus uses that reuse water for irrigation. A lot of facilities nowadays, they use this one. A lot of cities actually use that, reuse water for irrigations and other use than water than consumption. These are the climate zones in California, starting with close to Eureka is one, all the way, to the Southern California and then San Diego area that gets to 15 and 16, Coachella Valley and other things. Barstow area is 14, and so on. And each climate area has certain characteristics that energy calculations should use the hourly weather file from the specific zone where the building is located. Each weather file contains dry bulb temperature, wet bulb temperature, wind speed and direction, direct, normal, diffuse, horizontal, and global horizontal solar radiation. So it tells you that how much solar radiation you can get from that, the pressure and rainfall. We talk about the use intensity. There is another parameter that's not in use. It's called the time-dependent valuation parameter that's used to compare energy performance of the buildings or energy performance for different design. When we want to meet the certain compliance, it converts electricity, gas, propane to TDV energy, is dollar per kilowatt hour. It's hourly based dependent and is different for different type of building. It take into account the societal and environmental impact on hourly basis. So that was the difficult part of it, that when you want to use TDV, you have to calculate and show that when you save energy, how much reduction in carbon that you have, and the impact on society is, how does it impact on society? If you use less water, then how do you impact your local environment, and so on. It's not as used. TDV is not, there's a new version of it that is now trying to use, and it's also very comparable to energy use intensity. So you see energy EUI more often than TDV these days. So these are some TVD statistics summary for different climate zones, that, that these are the values. When you want to do the calculations, generally you want to be less or equal to these values, especially the average. So it gives you the range of the values for residential, non-residential 15 years, non-residential 30 years design. And then this is for natural gas, and this is for propane. It depends on the calculations that you do for the range, the energy that you use. So again, we talk about a lot of things. But any questions so far? No? Okay, we continue. You're getting a crunch on time. So I just wanted to talk about eQuest, a software, and then introduce you to another software. eQuest is a free software. You can download it from the Department of Energy website, and that's the address to do this, to be able to try with this. And the other one is called ComCheck. It's a web-based, that there are also, the PC-based version of it, that also that you can download to be able to do the simulations. So very similar to eQuest, this ComCheck also, it allows you to give a specification about the roof, whether you have a skylight or not, what kind of external wall that you have, what kind of internal wall you have, what kind of window and size you have, doors, what kind of doors, what kind of basement, what kind of floor, and so on. And then it switched to internal, lighting, external lighting, type of mechanical system and requirements. And this one is based on the ASHRAE, American Society of Heating and Ventilation Air Conditioning System, standard 90.1, which is for the buildings that is in collaboration with the Department of Energy. So you run this simulation to see if you meet that standard for rating. For the one before eQuest, I don't know, Scott, do I have time to go through the simulation or just talk about what are the windows? I think that if I bring up the slides, let me try to see that if I
You
can.
want to do it at the end, Hamid, if there's time?
Yeah, let's do this. I'll come back to this. I just want to quickly finish these. Okay, so let's just talk a little bit about the wind energy potential. Yeah, you have seen that wind energy in, wind farms in California. We have one close to Northern California, San Francisco area, one big one in Antelope Valley area, and one close to Palm Springs area. These are the ones. It's run by San Diego Gas and Electric and Southern California Edison and PG&E for generating electricity. Generally, it's more than 25% of electricity is generated by wind. These are the horizontal axis wind turbines. So in wind provides more than 10% of electricity in 16 states and over 30% in Iowa, Kansas, Oklahoma, South and North Dakota. US is the second in ranking after China in producing wind power. In 2020, the total power generated in the US from wind energy was about 122,000 megawatt. It's about 8% of the total power generated in the US. 43% of renewable energy is wind energy. And then on the right-hand side, it gives you the growth of the wind energy. And you can see China is very high. And then the next one is the US. And after that, it is Germany and followed by India. And then the rest of them much lower than that. In 2000, there was a simulation done by one of the PhD students at Stanford by Jacobson, Mark Jacobson. You can actually Google this. They wanted to see that what is the wind energy potential globally, how much it is. And they actually did a calculation for the standard wind turbine that has a diameter of 77 meters and is on a pole that goes to 80 meters high at this level. And they produced actually results for different regions. This is a sample calculation for California. And the idea is that they said that global wind power potential for the year 2000 was estimated to be 72 terawatts. As such, sufficient wind exists to supply all the world's energy need at approximately 15 terawatts, although many practical barriers need to be overcome to realize this potential. So obviously, at that high level, there is a lot of wind at that high level, but the challenge is that how do you capture that wind and transmit the energy to Earth or to the local area for usage. That is the challenge. There has been some design of using balloons, generators on balloons that is, go on high into the sky at that level to generate electricity. But it hasn't been realized. But it tells you how much potential we have. And we talk about also the solar potential in the US, how much solar potential we have that we can take advantage. So generally speaking, is that we have enough solar and enough wind potential to be able to meet our needs. That's basically what it says. Average wind speed, I just wanted to tell you that locally, give you an example of Zuma Beach in California, that percent of the windy day per month and the direction of the wind, it tell you that. Generally, you know, I'll talk about it in a moment, that if you have 6 meters per second or 14 miles per hour wind, you can generate electricity. So there are gusts, you know, of more than this level in many areas in locally that you can generate electricity. So that gives you an idea of the wind energy potential in some areas, just like a Zuma Beach, that it can be installed, depend on the design, to generate electricity for the city. So there are obviously San Francisco marina areas has a lot of potential there, and there are many other you know, areas within the urban environment that has this kind of potentials. So this is monthly wind speed statistics for Edwards Air Force Base, that in Antelope Valley, that you can see that the average is go from 10 to 16 and then go back down in different months. And then there is the gust of 30 to 26 to 30 miles per hour generated during these months that are, they have a lot of potential. So city of Lancaster, for example, have this kind of potential to be able to locally generate electricity, not just from the wind farms that they have close by, but also within the city. Around the buildings locally, we also have wind generated, you know, that when the wind comes, you know, if you look at the building structures, there are areas around the building, it become a wind tunnel area or wind corridor area, that it depend on design, it can be taken advantage and generate electricity. So basically, horizontal axis wind turbine, the blades are airfoil, they have high torque, efficiency 35 to 45%. They're made of fiberglass to reduce weight. There is an issue with recycling fiberglass right now with these, that you know, research going on is that how to come up with a way to recycle once they are decommissioned. Need a large open area for blades to rotate, cannot be placed near residential and commercial area, need to be aligned with wind direction for high efficiency. They are relatively narrow range of peak power, so they are controlled to in terms of RPM, so they can meet their maximum output. They have a complex control system. They are hazardous to bird and endangered species. Since it rotates, the bird do not see them and fly into the blade. So that's one major challenge for the wind farms. They're trying to come up with a way to mitigate this problem. Generally, areas with average wind speed of 6 meters per second or 14 miles per hour are potential site for wind power generation. Wind power is proportional to the velocity or speed to the power of 3. An increase in the wind speed from 10 meters per second to 12 meters per second results in 73% increase in power. And also, if you increase the sweep area, you know, and for horizontal, it is related to the radius or diameter of the blades. If you go from 10 meters to 12 meters, you have an increase in power of 44%. It's with elevation, the wind speed changes. So there is, this is the equation for that with respect to wind at this sea level. You know, when you go higher, I mentioned that if you go to high level elevations, the wind energy potential is there. We actually at the 80-meter height, we have a lot of energy potential. Alpha here is a roughness strain. You know, if you are close to water and ice, it's 0.1. It's a low grass and height. Low grass area is 0.14. So there's a constant that you can assign based on the surrounding area. And so if the height is doubled, the velocity is, or the speed is increased by 25% and the power by 34%. That's how you can see that you have towers for the wind turbines. It comes with the basic power curve. Each turbine shows the power produced at different wind speed. The power coefficient is the ratio of the power produced with respect to the available power, and it is the efficiency of the wind turbine. The location where the tower is mounted is important. The windmills are located at a place, when you look at the wind farms, they are in uphill. You know that as the wind comes, it actually accelerates. So the wind speed goes up as it goes slightly toward the hill before it decelerates close to the peak and then separate. So that's why that you see that the location where they put these towers are important because of the, the speed of the wind. And these are the sizes and the height: 10 kilowatt, 25-meter height, tower height 140, 25 to 50, 50, and so on. Then there is a vertical axis wind turbine that nowadays that has an efficiency of somewhere around 25%. It's not hazardous to bird. It rotates. It's a low energy production. It can be used in cities and close to the ocean and like Zuma Beach and other areas. And so these are different design that has been tried. And so these are very popular in Japan now. You see them often. And then I saw that actually European, especially, Australian, also European, they are using this on a big size on ocean platform. Recently, there is an experiment going on to design this, to use this on ocean platform as offshore wind turbines, the vertical axis ones in certain areas. This is what we designed, and we used, there's a company actually used these, our design in Puerto Rico right now. This is one installation on the buildings side that we are designing. We have designed, and it's based on the several patents that we produce based on. And the efficiency of this is somewhere between 30 to 40%, which is a very high efficient turbine, stackable turbine. And any questions so far? We have 5 minutes to 12. I wanted to go over quickly on the slides for the eQuest, and you got also the documents and overview and so on that you can study on your own. And also these slides will be emailed to you. So you have actually a link to go and download the software and play around with this. Any questions so far? I know I covered a lot of materials without the break or anything, and sometimes it's very tiring, but any question?
On the wind turbines, are they made out of recycled material? Because like you said, they came out with the smaller wind turbines, and I see those broken down and being replaced with the larger blades to produce more energy. So is the material that we are using to build these recyclable? I'm a real big recyclable fan, but I haven't seen them come down and be replaced yet.
Yes, I mean, there is, generally they are made of carbon fiber or, materials that are, the recycling of carbon fiber material is depending on the curing and depending on the type of glues used and so on, curing system used, is a challenging thing. Right now, there is actually research going on because composites are used for aircraft also, aircraft wing and other places. So there is ongoing research going on and how to recycle these so they can minimize environmental impact and how much energy is used to recycle this. Every time that you go to the recycling process, you have to use a lot of energy to recycle. So and also it has, extraction. If you're using any kind of chemicals in this process, then what would be the environmental impact of those chemicals? So there is an ongoing research going on, ongoing research in this area to how to recycle different kind of composite that we develop, rather than put them in landfill. It's an ongoing, it's a challenge. It's a huge challenge.
I'm kind of worried all the new technology that's coming out, we're jumping ahead and we're just mass producing it. And like you said, it's a new challenge. It's an ongoing challenge to recycle this material. Are we putting the cart before the horse? Because are we
Well-
polluting our earth with the aftermath of this? Are we doing more damage than what we are good?
This is a huge discussion, but I want to tell you that an example of the battery recycling that for the electric vehicle. When we look at the life cycle analysis of the energy used to produce electric vehicle, if renewable energy is used in recycling, then it's beneficial. In other words, that you are not really you are not generating a lot of carbon emissions to be able to carbon emission here to recycle materials. So the same thing applies here, that although there are processes that have been trying to recycle composite materials, if the electricity that comes from for recycling comes from renewables, then the impact is much less. Now, the other aspect of it is that to be able to separate curing glue and other things from the material, and also the shredding process, and then also reuse process. How do we do this? That's the big challenge in terms of the discarding the chemicals that used, and also that once we shred these, can they be recycled and reused? That is the challenge.
Well, thank you. I could probably go on and on with you
I
looking about
understand.
how we're going to recycle the material. Because like I said, I've been recycling from a very young age. And it just it worries me that we're just producing material and it's just for a short period of time, and it's just litter in our country, and we don't have the ability to recycle it and use it, at a later time. So
Yes, I understand. I understand.
so thank you.
Thank you. Thank you for your comment. So I am going to just quickly share with you a document that I have. Let me see. Yeah. So when you use eQuest, I don't know if, can you see my screen?
Yes, I can.
Okay. So these are the windows, we didn't get time to try it and input the the parameters in there. But that once you start eQuest, you get this kind of windows that you need to specify. So you identify, the type of building, the title of the building, the climate, the location site, and which utility company is using automatically come up, and so on. And then the address, and then the shape of the building. Either they have options to, import this, or actually click and select from the type. So I try this for the C-Pace building, which was an L-shaped building. And you put in the perimeter, zone depth and dimensions, and so on, and also the type of material, and it goes on. There are about 40 some windows that you go through. You don't have to select all of them, but you have to be familiar with what type of flooring you're going to use. You have a selection process, what type of insulation you're going to use, what kind of windows, where the windows are, what kind of doors, which direction the doors are, what is the outside area, what is the top floor, the distance between the floorings, what are all of these at the end. So once you have gone through these and select this, and the usage also identify, for example, for the different day, what kind of usage, for example, Monday through Friday, and also holidays and so on, the operation hours 7 a.m. to 11 p.m. And so on, and then different kind of system, different kind of air conditioning system that you can select. And I use chilled water because we use chilled water coil and hot water coil here, but there are options for different kind of system. You can also have a temperature, set temperature for cooling and heating, for low temperature, high temperature, for occupant, when it's occupant, what temperature should be, when it's not occupant, what temperature it should be, so you can reduce the load and so on. So you go through this. At the end, it gave you this. It gave you the building shape. It gave you actually the design of your system, HVAC system, based on the selection that you have done. It's lay out the system for you in terms of the type pumps and so on and what type you want. And it give you an output. It give you, for our case, majority comes from electricity and also gas consumption to heat the water based on the hot water system that we have. It give you that how much electricity you will use throughout on a monthly electricity that you have. So it give you this, and then it give you the total. And again, once you have the total, as I said, that you can convert them to BTU, kilo BTU, and divide them by square footage. And so that will give you energy use intensity. And then you can compare that design with the baseline design or your goal to see if you meet that goal. If not, then you go back to these building through these windows and choose different kind of system, different orientations, and so on. So it gives you a chance to play around with these parameters to reduce energy consumptions. This one is is not as user-friendly as the other one that I mentioned, that I gave you the linkage, and that one also. But you need to know the information about your building before you can do that. So I just wanted to stop here. It's 11:05. It's 5 minutes past. And any last question that you have or any discussion that you would like to have?
No, I want to thank you, sir, though, for your time and your knowledge. I appreciate it.
Thank you so much for attending this time. I appreciate that. Okay, if not, then have a great day. I'm wishing you all the best, and hopefully I can see you in the next podcast or next webinar.
Thank you, sir.
Thank you so much.
Thanks, everyone.